This is part 1 of the chapter 13 lecture videos. I have divided it into 4 sections, in part just to have smaller sections and not just one big lecture. So that way, if I make a mistake, I only have to correct a smaller section and not a whole big section. So we're going to start in part 1 by talking about some of the properties of liquids. Part 2, we talk about the heating curve. Part 3, we talk about intermolecular forces and how they impact the properties of a liquid. And then in the 4th part, we just mentioned 2 vocabulary words, hydrate. Oh, and I guess it's not a vocabulary. We talk a little bit about some of the uniqueness of water. So those are the 4 sections, and let's jump into part 1. So in the gas chapter, the previous chapter, I had bullet points that gave us an overview about gases. And so this is the one for liquids. So I think we started thinking about this in our class in chapter 1, but here are what it is now in chapter 13. And so I'm hoping that a lot of it sounds familiar. So liquids have a definite volume on the first bullet point, and just so you understand, a definite volume means the volume does not change depending on its location. So as an example, if I have 20 milliliters that I measured in a beaker, and then I poured it into a graduated cylinder, while the graduated cylinder would give me a more precise measurement, I would still have close to the 20 milliliters. Now, we worked with measurements knowing that a beaker is less precise and less accurate than a graduated cylinder. However, the volume's really not going to change. If I have around 20 milliliters in a beaker, I should have around 20 milliliters in a graduated cylinder. That's what we mean when we say we have a definite volume. Now, fluid shape, that means that the liquid can change into the shape of the container. Now, not like a gas where it fills the container, but where the liquid is touching the container, it will take on that shape. Again, I refer back to things we've done in lab. So if you have a beaker and you pour 20 milliliters into a 100 milliliter beaker, you would measure it up to the line and it would have that shape of the beaker, the circle, and it would go up just a little bit on the side. Then if you got a 25 milliliter graduated cylinder, which is a tube, a cylinder, and you poured it, now those 20 milliliters would look like they're in a cylinder. That's what it means when they assume the shape of the container. It's fluid. The molecules can flow past one another. So then the third one does say the particles are close to one another, but they have fluidity. So gases, if you recall from the previous chapter, are really far apart. There's a lot of space in a gas compared to how small the particles are or how big the particles are. There's a lot of empty space. But for liquids now, they're closer together, but not held rigidly. There's enough energy in a liquid that they pour, and that's what it means to be fluid. They can flow past one another. I always think about how you can walk through air, like just walk down your hallway, and you might feel air or the air moving past you as you walk, but you easily walk through it, right? There's lots of empty space. If you have a swimming pool or you go, well, the ocean's a whole nother thing because that water's really moving. So let's go into a swimming pool and you walk through the water. You still can walk through the water because the particles flow and will get out of your way. But now there's a little more resistance because the particles are closer to each other. So you have to use some of your energy to kind of push those particles out of the way. Now, the fourth one here, close contact, that is just telling us that the particles are close to each other. And then the new one, so this is new, right here. So we haven't talked about this before, but liquids have significant attractive forces. That means the forces like little magnets that hold the particles together. I mean, they're close together. They want to be next to each other because they are attracted to each other. And we call these attractive forces between the particles intermolecular forces. And I will go over the 3 intermolecular forces that we're talking about in class in part 3 of the chapter 13 notes. So that's something that we're going to learn about this lecture, and we're going to learn how those intermolecular forces influence some of the properties of liquids. So let's look at the properties of liquids. So on this sheet, I listed some of the properties that we could encounter in this chapter. We are going to go over more specifically vapor pressure, boiling point, and freezing point. So I'm not going to just read this slide to you. I would like you to be familiar with these different properties, but since we're going over 3 of them in detail, I'm going to move on to that. So what I would like you to know from this slide is these properties and have a general idea about when we use this word, what are we talking about when describing a liquid. So before we talk about vapor pressure, which is going to be the first property we talk about with a liquid, we have to remind ourselves about evaporation and condensation. So when we have a state change between a liquid state and a vapor state, the words we use are evaporation, when we go from a liquid to a vapor. That's called evaporation. That's what it would mean. And then condensation is when we go from a vapor to a liquid. And so liquids can do both depending on the situation, or liquids and vapors. They can go from a liquid to a vapor or from a vapor to a liquid. I guess I shouldn't say liquids can do both. I can say a substance can do both. It can go evaporate and condense depending on the situation. So they have 3 little Erlenmeyer flasks down here, and I want to just look at the pictures, even though I know they're kind of small. So letter A in this flask, this is describing evaporation. And notice that the container's open, and so what's going to happen is as the liquid evaporates into the vapor phase, the vapor will just keep moving like gases like to do to fill a container. So it will move right on out of the flask into the air, never to be seen again. Well, at least not in this flask. And so a few things I want to point out. And one, so they're using little arrows to express the evaporation. So see, they have 4 little arrows. And when a substance evaporates, it's actually layer by layer. So only the top layer can evaporate. Notice all of these little particles, little molecules, like maybe it's water. All of these little water molecules, we'll just say, they could be moving around and they could have energy, but they aren't evaporating because they're kind of trapped by the other water molecules. So evaporation is a layer by layer process. So the top layer is the one that's able to escape into the vapor phase. Now the second picture, what they did is they capped the Erlenmeyer flask. So now the vapor cannot just continue on out into the air, but it's trapped inside the container. And so what happens is a liquid will evaporate as it gets enough energy to break free from its liquid and turn into a vapor. But if it loses some energy, whether it collides with another molecule, whether it collides with the sides of the container, whether in its motion it simply goes right back down and hits the liquid, if that vapor loses energy, then it will go from a vapor back to the liquid, which is then called condensation. So you'll see here they still have 3 arrows pointing up, and only one arrow pointing down. So in picture B, it's kind of at the beginning of the process, and still most of it is evaporating, but we now are getting some condensation. And you probably see this if you've ever had a water bottle in a hot car, because if you leave it closed, you'll see the condensation on the sides. So that's just from as the liquid water turns into vapor and then loses some of its energy by colliding with the wall, then it will turn back into a liquid. And then finally, this letter C, which is still the closed container, but it's over time, it's reached what's called an equilibrium. And you may not be able to see the little words on the screen, but it says the rate of evaporation equals the rate of condensation. So eventually, if you leave a container closed, what happens is how fast it's evaporating equals the how fast it's condensing. And so now if you notice, it has up one, down one, up one, down one, up one, down one. So over time, as much as evaporating, it's condensing. So to our eye, it actually looks like nothing's happening, but it's a continual active process. It's not static. So you can get this evaporation, this equilibrium. And that equilibrium has to do with vapor pressure, or how they measure vapor pressure. So let's take a look at vapor pressure, which has to do with evaporation of a liquid. So the vapor pressure is the result, or measured when you have an equilibrium between the liquid and the vapor. So you have that rate of evaporation equals rate of condensation. Now, when we think about a vapor pressure, it's what I put in words here. It's the pressure of the vapor in red, the pressure of the vapor resulting from the evaporation of a liquid above the sample. So when we say vapor pressure, oftentimes people go back to thinking about the gas and think about gas laws. And we know in gas laws, the pressure is created by the gas particles hitting the sides of the container. But vapor pressure really is not a property of the gas, it's a property of the liquid. And as the liquid is evaporating, those vapor molecules that are the result of the evaporation create a pressure, and that's what we call the vapor pressure. Now notice, and we'll talk about it a little bit more, this bullet point says it doesn't depend on how much liquid you have. Okay, so it's independent on how much. It does depend on what the liquid is. The vapor pressure will increase with temperature, and that's because the higher the temperature goes, the more energy they have and the more liquid will evaporate. We'll talk about that on the next slide some more. And the boiling point of a liquid is directly related to its vapor pressure. And so on the next slide, we're going to talk about boiling point, but I want to draw how I kind of illustrate vapor pressure, because for me, when I was learning chemistry, especially introductory chemistry, it was helpful in my mind, imagination, to kind of have something to hold on to. So if I'm going to have two containers here, and they're going to be with two different liquids. And we're going to say, even though I may not draw it this perfect way, we're going to say that both have the same amount of liquid. It's the same container and the same amount. So this is going to be liquid A. And then over here, I'm going to have liquid B. So what happens, or how I understand vapor pressure, is the liquid evaporates, and I'm going to draw that as arrows. These are my liquid molecules turning into a vapor. So above here, what's created by the liquid is the vapor pressure. So as the liquid escapes into the gas phase, it creates a pressure. And so that's how I'm imagining it, is that liquid escaping into the vapor and creating a pressure as it escapes. Now, my liquid B is a different liquid, same amount. They can even be at the same temperatures. And this is my liquid B. And so it's also escaping, and my little arrows here, this is creating a pressure. That's my vapor pressure for liquid B. So as the liquid evaporates, it creates a pressure above the liquid. And so when we look at it, not all liquids are the same. In fact, an important thing that differentiates them are their intermolecular forces, which we'll learn about in part 3. But what I can say is I would describe this as having a higher vapor pressure because it has a lot of gas escaping. And something like this would have a low vapor pressure. So it depends on the liquid. And we'll talk about temperature in just a minute because it does depend on the temperature. On the next slide, we'll talk about temperature. So from this slide, what I want you to kind of wrestle with is how would you describe vapor pressure and how can you get a handle on what vapor pressure is. And you can go to other websites, you can do other things. This is something that is in a way abstract for people, so sometimes it takes a few different ways of thinking about it until you have one that will settle with you. Now, vapor pressure, the reason it's important, or one of the reasons, is that vapor pressure is directly related to boiling point. And so this slide is on boiling point. And if we look right here, boiling point, or the temperature where something boils, is when the vapor pressure of the liquid equals the external pressure. And so most commonly, the external pressure is the atmospheric pressure. So let me give you an example. I'm going to have a container, and we'll say it's water. And this is just at room temperature. So even at room temperature, water is evaporating. So there's my water. It has a vapor pressure, even at room temperature. And here, the atmospheric pressure is the pressure pushing down onto the liquid. It's pushing down on everything, but we're thinking about the liquid. And that atmospheric pressure is what they're talking about as the external pressure outside of the liquid. So the atmosphere is pushing down, and by this first diagram at room temperature, the atmospheric pressure pushing down is much more than the vapor pressure, the evaporation off the liquid, and so water doesn't boil at room temperature, right? Okay. So now let me redraw my water. And it's going to be the same water. And I'm going to heat it up to 100 degrees Celsius. And we'll talk about that number here in just a minute. So, sorry, my pen. There we go. This is also water. And I'm going to heat it up. And we've done this enough in lab. It's not super exciting. And I'm going to draw, again, 7 arrows down. I got to squeeze one more in. Okay, so there's my atmospheric pressure pushing down. Now, originally, I had 3 escaping. That was at room temperature. And as we heat up the water, more liquid starts to evaporate. And at some point, you even start seeing steam. So more will evaporate. Then another one evaporates, and more evaporates, and more evaporates. And eventually you reach a temperature for water. It's 100 degrees Celsius. We'll talk about a little more specific with that. You reach a temperature where the external pressure, which in our case is the atmospheric pressure, so everything pushing down equals the vapor pressure. Everything pushing up. And what happens is the liquid boils. That's the temperature that the liquid boils. So once you get the vapor pressure equaling the atmospheric pressure, it will boil. Now this 100 degrees is a little bit of false advertising because it really needs something more specific. 100 degrees is here in the middle. This is something called the normal boiling point for water, and that is when the atmospheric pressure or the vapor pressure is 1 atmosphere. So when the vapor pressure and the atmospheric pressure, when it's 1 atmosphere, that is the boiling point. And this occurs, 100 degrees is at sea level for water, not for all chemicals. So Jacksonville is at sea level. We're at 1 atmosphere. So our vapor pressure is at 1 atmosphere around 100 degrees. And so, but if you go up to a higher elevation, higher elevations, there is less atmosphere. So there's lower external or atmospheric pressure. If I could spell atmospheric, it would be good. And so if there's lower atmospheric pressure, it doesn't take as much energy to have the atmospheric pressure equal the vapor pressure, so we have lower boiling points. So in places like Denver, Colorado, or where I grew up, which was 7,000 feet an elevation, the water boils it can boil anywhere from the low to mid 90s. So boiling point is not constant over everywhere. It's locationally has variation in it because it has to do with the external pressure. And if you're just curious, I'll mention it because NASA has videos of water in space boiling, and without atmosphere, it literally just boils. Like it's not even hot. It looks like hot boiling water that we have in lab, but it's just boiling at whatever temperature they have the water at, because without atmospheric pressure, the water already has enough vapor pressure to boil. And I've used water as an example for all of my illustrations because it's something we're familiar with. But all liquids would have something similar. They don't all have the same boiling points because they don't all have the same vapor pressures. So I have just used water as an example because we're familiar with it. All right, so let's look at melting. Now, melting and freezing, excuse me, which are when we go from liquids to solids. So when we go from a solid to a liquid, we melt, and a liquid to a solid, we freeze. Now, these are not impacted by vapor pressure. So solids are not impacted by that. So really here, we just want to think about the words. Now, what's interesting, if you think about it, freezing point and melting point are the same temperature. So, for example, for water, the freezing point and melting point is 0 degrees Celsius. So I'm freezing it if I'm getting colder. So if I'm going from a higher temperature to 0, that would be freezing. Going from a liquid to a solid, I would be melting if I was warming it up. But it freezes and melts at 0 degrees C. And here is something that we're going to take forward and look at in part 2 of the videos. And that is, you can have two phases present, like a solid and a liquid. And as long as two phases are present, the temperature is going to stay constant. And we're going to see this in a graph. But when you have solid and a liquid together, like ice, water, it will stay at the freezing point until all the ice has melted, and then it will start to warm. That is because any energy is going in to melt the ice and not change the temperature. And we're going to investigate that idea a lot in the second part of the video, and this will be our only part of the with the calculation. So in this part, what you need to know is just freezing point and melting point, the definitions, and we're going to begin that thought of if you have two phases. And let me just restate a phase. We're talking about solid, liquid, and vapor. Those are the three phases when they're in that state. As long as two phases are there together, the temperature is going to hold constant. All right, so I just wanted to make sure that is about properties of a liquid. So to get prepared for this part of chapter 13, review the words, make sure you know what the properties are talking about. It's particularly important to know about vapor pressure and to know about how vapor pressure influences the boiling point. Like, what's the relationship between vapor pressure and boiling point?